A related concept similar to the idea of Indianness is what's called alignment, right. In alignment, what we are trying to say is, I have 4 bytes, and if I said that the address of x was 0, then what that would mean on a little Indian machine would have meant that mem of 0 would have had the least significant byte 78 hex of course, and mem of 3 would have had the most significant byte. So far so good, we already saw some examples of how that would get implemented. Is it also possible for me to have another setup where the address of x is 2, okay? And what that would correspond to is that mem of 2 would have the least significant byte, mem of 3 would have the next one, and mem of 5 would finally have the most significant byte, that is 0x12, right. It turns out that this is a bit problematic, right. Why is that? Because a CPU bus is typically either 32 or 64 bits wide, okay, which means that reading 4 bytes 32 bits from memory at a time is easy. I can basically take in a chunk of values mem of 0 to mem of 3 at one shot, or I can take in mem of 4 to mem of 7, or if I had a 64 bit bus, I could take mem of 0 all the way up to mem of 7 into the CPU register at one shot, right. But what happens when I want to read the values mem of 2 to mem of 3 on a 32 bit machine? Right, what would end up happening is, I would need to read in a 32 bit chunk of data from mem 0 to mem 3, because that is how I get the data in a chunk of 32 bits, right, starting at location 0, and I would need to have another 32 bit value which reads in from 4 to 7, and then I would need to take 2 and 3 from one of them, 4 and 5 from the other, and rearrange to get the 2 to 5 4 bytes out, okay. Now this might sound like a trivial thing to do, and it is for us when we think about it. For a computer, it's not that it's necessarily hard, but it is harder than just pulling out 4 consecutive bytes, simply because it needs to take one extra step of operation, right, which means that it will probably run slower. It's not that it can't be done, it's just that it's more likely going to be a bit slower than if I had given my address always as starting from 0 or 4 or 8 or some multiple of 4, because that is what the CPU would be able to read out easily, right. That is basically how the computers are constructed more than anything else, right. Now you might ask what happens about 64 bits, because after all I can read in 0 to 7 at one shot, so then extracting the 2 to 5 from that should not be difficult. Yes, until I ask, okay, what happens if I wanted to go from 6 to 9, right, mem of 6 to mem of 9 in order to store a 32 bit value, right. Then I would need to read mem of 0 to 7 at one shot, 8 to 15 at another, and once again do this rearrangement. It's not that it's impossible, it can be done, and computer circuits are good at doing this kind of stuff, but it makes it slightly slower than if I had just directly stuck to this multiple of 4 business, okay. And effectively what we say is that choosing your addresses such that it's a multiple of the size of your data type is what is called alignment, okay. And in this particular case what we are saying is, if my address is actually a multiple of 4 for a 4 byte data, that means it is properly word aligned or integer aligned, right. If it was an 8 byte int 64, then my address would have to be a multiple of 8. If I had some other data type that is of size 16 bytes, I would want my address to be a multiple of 16. Generally speaking, we are not particularly concerned about data types that are of 6 bytes or 7 bytes or 3 bytes, right. Our alignment issues are more to do with the fact that I can read in chunks of these powers of 2, okay. So the alignment is more to do with either 4 bytes, 8 bytes and so on. It could also be at a larger size, which is called usually a page, which might be 1 kilobyte in size even, okay. So I might have like large data structures that actually get page aligned, meaning that the address for that has to correspond to a multiple of 1024, okay. Now this alignment once again is not something that is enforced by the language, right. It is quite possible that some compilers and some architectures will allow you to have an integer which is starting at location 2, right, whereas others will not, they will actually read the data wrong. So this piece of code over here is a slightly complicated example of what happens when we try to misalign integer, right. Now it makes use of a couple of different things. One is the fact that if I declare one integer a, give it the value 1 2 3 4 5 6 7 8, and then I declare another integer b immediately after that, then in this case it turns out that the address of a and the address of b are going to be adjacent to each other. This is actually not guaranteed, right, by the compiler, but in practice it is almost always the case, right. It is not something to rely on, but we are going to just use that for our demo over here. In any case, what I will do is I will print out the value of the addresses for a and b out here, right. So let us quickly take a look at that first. In this case what I have done is I have printed the addresses out in hex format, right. So this %08 basically takes the address, pads it out to 8 characters, right, at least 8 characters. In this case it actually turns out that the address corresponds to more than 8 characters. It is a 64-bit address which would need 16 characters to represent, right. So it actually spills beyond that, but it does not matter, it sort of shows the number in hexadecimal. And what you can see is that the address of A is something something 18C and the address of B is something something 188, okay. And the interesting thing out here actually is that if you think about it, even though A was declared first, right, it has a different address, or rather it has a higher address, right. 18C is a number that is bigger than 188, okay. A has a bigger address than B, right, which was declared later, and this is because of the way that the program goes about allocating variables, right. It uses something called the stack, and the stack in these C programs is assumed to grow downwards. The first variable that you declare is the highest element in the stack, then the next one, then the next one, and so on, okay. So now that I know that the addresses corresponding to A and B are these two values, by the way you will notice that when I run the program again, right, I get a different set of addresses, right. It was some 18C and 188 last time, now it is some C0C, C08. In fact, each time that I run this, if I just click on run, it is going to give me a different set of addresses, 90C, 908, right. The point is there is no guarantee on what address you will get. This is something called a virtual address that is created by the operating system. It changes every time the program is run, right. So at no point in a normal program should you be relying on the fact that you have a fixed particular address that you have access to. You cannot guarantee that, okay. In embedded systems that can actually become a problem because I sometimes do need to access a specific location in memory. There are ways of getting around that, but by default every time you run a program you end up in different locations in memory. So now we know anyway that A has an address higher than B. What I am trying to do is a complicated way of getting an address which is somewhere in between these two, that is in between this 908 and 90C, and if I think about it, that should probably be 90A, right, which is between 8 and C. 8 is the number 8, C is the number 12, A is the number 10, which is in between those two. So how do I do that? I first take the address of B, I treat it as a character pointer, I add 2 to it. Why did I have to do all this? Because if I tried directly adding 2 to the int star, I would end up with something different. We will get to that later when we talk about pointer arithmetic. For the time being, you need to do this, right? You need to basically first make it a character, go 2 bytes up from there, and then treat that as an integer. Okay. If you find this confusing, please spend some time trying to understand what is going on over here. Once you get it, this will make your entire understanding of pointers a lot simpler, right? And it's worth sort of thinking about and making sure that you understand exactly what is happening out here, right? Like I said, you take the pointer to B, you get its address, treat it as a character, pointer to a character, add 2 to it so that I go from the 08 up to 0A. Now say, okay, I have got this value D which is pointing to this 0A address, but now I want something which takes D but treats it as an integer, right? And there I declare int star P and say that that should be basically take the value of D but now treat it as an integer pointer, which means that when I try dereferencing P, right, star P, I will get a 4-byte value. And sure enough, what happens is I find that the address of P which I have printed out here is actually this values with A, 90A, right, exactly halfway between this 908 and 90C. And what is the data in P, right? That is what I get by star P, dereferencing P. Now I am going to treat it as a 4-byte integer. I actually get the value 5678. How did that happen? It got 2 of the bytes from A, right, and then it got the ABCD which are the 2 bytes from B. Okay. So in this case what has happened is that the alignment went ahead, the compiler got this through for you, it accepted an integer which is not properly aligned. So in most cases you can actually do this, you can actually access data which is not aligned properly on a multiple of 4. There are 2 things to keep in mind. Number 1, it is marginally less efficient than if it is actually aligned properly, because if I had an address that was properly aligned, I would need to just read one value from memory in order to get the integer, whereas here I actually need to read 2 values in order to reconstruct that integer. The second thing is, if you have a big endian versus a little endian or a top down versus left to right kind of memory model, you could end up with different values out here, you might even end up with the wrong value. Okay. So all of those are sort of things to keep in mind when you are trying to do different things with the alignment of pointers or alignment of data. For the most part, it is better not to try and mess around with those until you are absolutely sure of what you are doing, right. What is important though is to be able to switch between the name given to a memory location and a pointer to that memory location, and to realize that they are both effectively dealing with the same thing,